The ground begins to tremble. First, a subtle vibration felt through the soles of your feet. Then a deep, resonant hum that travels through the earth. It is not an earthquake. It is the signal, carried along two narrow strips of steel, announcing an arrival minutes before anything is visible. This is the signature of a different class of machine, behemoths of iron and steam engineered to move hundreds of tons of cargo through scorching deserts and frozen mountain passes. Their entire existence was a battle against physics, immense weight balanced on a knife's edge of polished steel, generating colossal power from controlled explosions, pure mechanical force. They were machines built for motion, yet some were so paradoxically massive they tested the very limits of the infrastructure designed to carry them. What kind of engineering creates a locomotive so powerful it becomes its own greatest obstacle? Prepare for a journey into a lost world of mechanical giants. The age of extreme engineering begins now. The introduction promised machines capable of surviving extreme conditions. But what if the main threat isn't frost or mountains, but the complete absence of water for hundreds of kilometers? In 1953, South African engineers revealed their answer, a machine built not for speed, but for pure survival, the Class 25 locomotive, born for the desert. Unlike the sleek express engines of Europe, this was a brutal, utilitarian beast. Over 210 tons of dark, heavy steel. It generated 4,200 horsepower, designed for one task: to haul immense loads across a landscape that killed other machines. The air is motionless, shimmering with heat. Against this silence, the locomotive is a constant mechanical hum, a rolling factory in the middle of nowhere. Its secret was not raw power, but a revolutionary condensing system, a closed loop of survival. First, hot exhaust steam from the cylinders is piped into a gigantic tender, a radiator the length of a train car. Next, huge turbine fans pull the bone-dry desert air through the system, forcing the vapor back into precious liquid. Finally, that reclaimed water is fed directly back into the boiler to be used again. The cycle is closed. This engineering feat saved up to 90% of its water. Its range was extended to 800 miles. That's the distance to cross the entire Kalahari Desert without a single stop for water, an impossible journey made possible. This was not about breaking records. It was about defying the environment itself. The legacy of this machine extends far beyond the desert. Its design was so effective, so radically efficient, that it found an unexpected second life. Ironically, in the 1970s, Soviet engineers studied this desert technology for use in the extreme cold of Siberia. If the South African Class 25 was born for survival, our next hero, appearing 17 years earlier, was created for pure speed. In 1936, Hungary challenged not the desert, but time itself, creating a locomotive that seemed like a visitor from the future, the MAV 242.001. This was a machine built around a single radical principle: smoothness at extreme velocity. Its heart was a four-cylinder engine generating 2,300 horsepower. The process was elegant. Steam is fed into four cylinders, each firing in a precisely offset sequence. This distributes the massive forces evenly across the driving wheels, actively canceling out the violent vibrations that shook other steam locomotives to their core. The result was revolutionary. At speeds over 150 kilometers per hour, passengers felt not a shudder, but a smooth, effortless glide. A sharp, piercing whistle, followed not by a roar, but a quiet, confident hum. Visually, it was a blue arrow with silver accents, its aerodynamic shell slicing through the air. Its top speed, 152 kilometers per hour. In 1936, this was faster than most production cars could manage on a perfect highway, a technological marvel that shattered regional speed records, an engineering triumph, and a commercial failure. This technological masterpiece, which broke records and outran its own time, remained in history in the quantity of 1 unit. Elegance and speed are one extreme of engineering thought, but what happens when ambitions push designers to the other? If the Hungarian Express was a work of art, then the Soviet giant AA-20-1, built in 1934, became a monument to the idea of bigger is better, and its deafening failure. The goal was brute force logic: replace several locomotives with one colossal machine. The result was a steel behemoth with a wheel arrangement of 4-14-4, 14 driving wheels. The locomotive weighed over 260 tons, the equivalent equivalent of 4 modern battle tanks on a single rigid frame. This size was not an advantage, it was a fatal flaw. The machine was simply too long and too heavy for the infrastructure it was meant to serve. On a standard track switch, its immense, unyielding frame would literally fight the rails. The wheels would lift, the steel would scream, the giant would fall. This was not an occasional problem. It was a fundamental engineering dead end. The locomotive that was built to conquer the rails was being defeated by them at every turn. After several failed tests, Europe's largest steam locomotive was quietly sent to a siding and then silently dismantled for scrap. While European engineers often pursued sheer size, American design focused on mastering specific tasks. They created icons, and the first was an icon where speed and elegance were pushed to their absolute limit. The Norfolk and Western 611. Launched in 1950, a machine where precision engineering became art. Its streamlined black shell, accented with a single crimson stripe, suggested effortless motion. It looked light, it looked graceful, but hidden beneath that polished skin was a high-pressure boiler generating over 5,100 horsepower. This power was not for brute force, but for speed. It was engineered to pull a full load of passengers at speeds reaching 140 kilometers per hour, a technological breakthrough for its time. On board, the ride was impossibly smooth, but outside, its legendary whistle didn't just warn, it sang, a clear, melodic note that echoed across the Appalachian valleys. The locomotive remains an operational piece of history, but a moment from the 1980s captures its true capability. A helicopter flies alongside, its camera trying to hold the massive engine in frame, but the 611 accelerates, its drive wheels a blur. The locomotive pulls away from the aircraft, the camera shot shaking with the effort of pursuit. A frantic gesture from the pilot to the engine driver. The request was simple: slow down. The N and W 611 had to be held back because the film crew's helicopter could not keep up. But if the Norfolk and Western 611 was the queen of speed and grace, the giant forged by Santa Fe in 1930 was its complete opposite. A machine built for brute force with no interest in elegance. This was the Santa Fe 5000. It offered no gloss, no flowing lines, no chrome, just black, soot-stained metal, rough welds, and the raw mechanics of power exposed to the elements. It wasn't designed to be beautiful, it was designed to work. Its weight exceeded 226 tons, the equivalent of 4 modern Abrams tanks set on rails. All that mass, over 500,000 pounds, was concentrated on 10 massive driving wheels, a configuration engineered for a single purpose: maximum traction. The engine generated 5,600 horsepower, tasked with conquering the steep mountain grades of the American Southwest. Workers, with a touch of irony, nicknamed it Madam Queen. Despite its overwhelming effectiveness, it remained a one-off, a unique monster that proved one machine could do the work of several. But what if the task is not to pull weight, but to punch a path through nature itself? For this, engineers created a machine that hauls no cargo, a machine whose only purpose is to destroy. This is the rotary snowplow, a 135-ton weapon pushed into the heart of the storm. Its mission is to confront 10-foot walls of solid, compacted snow and obliterate them. The process begins with a sound that can be heard for miles, a symphony of industrial hell. First, the low, deep roar of a diesel engine, a 2,000 horsepower unit that moves nothing. It only powers the weapon at the front. The machine slowly presses against a wall of white. Then the rotor engages. Steel blades begin to spin, their high-pitched scream tearing through the air as they bite into solid ice. It doesn't push the snow, it consumes it. The massive turbine pulverizes tons of frozen mass into a fine powder, then violently ejects it over 100 feet away from the tracks. It is a controlled explosion of snow and ice, clearing a path that would take conventional plows weeks to open. This is not a locomotive. It's an instrument of force. The entire structure is armored steel, designed to absorb the brutal impact of hitting a solid, frozen obstacle at speed. It was the only answer to the blizzards of the Rocky Mountains, which could bury entire trains overnight. Even in the 21st century, its brute force solution is sometimes irreplaceable. During the record-breaking Wyoming blizzard of 2011, one of these machines was brought out of retirement to clear a blocked main line. Brute force against the elements and elegant speed seemed like two separate paths. But in 1943, Union Pacific engineers attempted to merge them, creating the Challenger 3985, a machine designed to be both powerful and fast. For decades, it held a singular title: the largest operating steam locomotive in the world. The secret to its balance was the articulated frame, a 4664 wheel arrangement. Two sets of driving wheels moved independently under a single massive boiler, each with its own pair pair of cylinders. This allowed the giant, weighing almost 270 tons, to flex on tight mountain curves, maintaining traction where a rigid locomotive would simply derail. The result? Over 5,600 horsepower, a titan longer than a blue whale, engineered for the harsh terrain of the American West. On one famous run, it covered 1,200 miles without a single mechanical failure, proving the perfection of its design. But even this masterpiece of engineering balance was only a step. If the Challenger was the peak of versatility, the next machines were built for one purpose: to be the most powerful in history. And the first was so heavy it broke the rails beneath it. This was the Allegheny H8, a mountain of moving steel engineered by Lima Locomotive Works to wage war on the Appalachian Mountains. Its mission was not merely to transport, but to dominate. The engine delivered a staggering 7,500 horsepower through an articulated 2666 wheel configuration. Its sheer mass was a force of nature, 386 tons. This wasn't just a locomotive, it was a geological event on wheels. When the Allegheny thundered past, the ground itself would tremble. The colossal weight was so extreme, it physically bent the steel rails beneath it. The machine was a threat to the very infrastructure it was built to serve. After one of these titans passed, maintenance crews had to follow, inspecting the line for damage. Only 2 of these giants survive, one now a silent titan at the Henry Ford Museum. Still think 7,500 horsepower is the peak? Think again. Allegheny proved that brute force has its price. But what if you combine power with engineering genius? In 1941, a locomotive entered the scene, whose name became synonymous with the word legend: the Union Pacific Big Boy. Its purpose was absolute: conquer the steep grades of the Rocky Mountains alone, without helper engines. The scale is almost incomprehensible: 1.2 million pounds, 548 tons of steel, water, and coal stretched over 132 feet. That is the length of 8 passenger cars in a single moving machine. The challenge was immense: how to make a titan of this size navigate the winding mountain passes. The solution was pure engineering elegance. The genius was its articulated frame, a 4884 wheel configuration. This meant the locomotive's chassis could literally bend in the middle, allowing 2 massive sets of driving wheels to act independently, a monster of 2 halves. This combination of mass and articulation delivered unparalleled traction, but it also delivered speed. Despite its scale, the Big Boy was no slow brute. It could reach 130 kilometers per hour, an impossible speed for such a colossal machine. By the late 1950s, the age of steam was over. Most Big Boys were retired, left to rust in museum yards. For decades, number 4014 was a silent monument. Then, in 2019, a monumental restoration began. Engineers swarmed the cold steel, sparks from welders dancing across the boiler. And then, the first exhale of steam, the deafening roar of its whistle, a sound that shakes you to the bone, mingling with the smell of hot metal and coal dust. The king had returned. Today, number 4014 is the largest and most powerful operational steam locomotive on the planet, a moving icon of American industrial ambition. To see it in motion is more than watching a train, it's witnessing history roll by. The Steam King Big Boy seemed eternal, but history has no time for eternity. While steam giants thundered across America, their executioner was born in the labs of General Motors, a machine running on entirely different principles. In 1969, it hit the rails. They called it Centennial. This was not a romantic giant, it was a cold, calculated predator. The colossal yellow body hides the core of its brutal efficiency. A single frame, but inside, a radical concept. 2 independent General Motors V16 diesel engines sit side by side. Each engine powers its own generator and drives its own set of axles, effectively splitting the machine in half. It was not one locomotive, it was 2. The result is a constant, smooth delivery of power, 6,600 horsepower, almost the raw force of a steam titan, but without feeding an insatiable firebox tons of coal and water every few hours. This machine doesn't scream with chaotic clatter, it hums, a deep, low-frequency thrum that you feel through the ground before you hear it, a sound signaling the arrival of a new industrial age. It was designed for speed and endurance, hauling high-priority freight across the vast American plains. Its engineering was so robust, its frame so durable, that NASA once used one for vibration testing. But its true legacy was written on the rails, day after day. The great steam engines were complex and required constant maintenance. This diesel predator was built for one purpose: to run. Many of these units remained in active service well into the 1980s. The low hum of diesel silenced the steam era's final whistle. But this was not an execution. It was a transition. From machine into legend. Big Boy, the breathing titan of fire and water. Centennial, the cold predator of oil and electricity. They seem like rivals from two separate ages, but they are chapters in the same great saga. These were not just locomotives, they were the engines that powered economies. They were the steel spines that moved nations forward. Each was an answer to the same challenge, an icon of power and ingenuity forged for its time. Two giants, one legacy. The real question isn't which was better, it's about what they represent. So we turn the question to you. If you could see one of these titans thunder down the tracks again, which would it be? The steam legend or the diesel king? Which machine is the true icon of ambition in your eyes? Leave your choice in the comments below. We read them all.